Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. So in the last lecture, we have discussed the very simple descriptors, and also we have discussed the shape number. So in today's lecture, we will discuss that how we can compute the shape number of any arbitrary shape. So what we can do to compute the shape number of any arbitrary shape, we will normalize the grid orientation by aligning the chain code grid to the basic rectangle. Okay, so the first step is to compute the basic rectangle of any shape that already we have discussed in the last class. So for that, we have to compute the major axis, and the major axis is nothing but the line joining the farthest point. Okay, so this is our major axis, and perpendicular to this major axis, this will be our minor axis, and we can create a rectangle using these minor axis and major axis. So this rectangle is called the basic rectangle. Okay, then we will align this basic rectangle. That means the major axis will be along x-axis and the minor axis will be along y-axis. Okay, then we subsample this shape using the grid operation. Okay, so when we divide this image in different segments, that means in different grids, then we will obtain this type of boundary representation of this shape. Okay, so now you know how to write the chain code, differential chain code, and the shape number. Okay, so for this shape, if we will consider the 4 directional chain code, then we can write 0 0 0 0 3 0 0 3 2 2 1 2 2 2 1 2 1 1. Okay, so when you will write these numbers in sequence, circular sequence, then you will obtain the chain code. Okay, and we can compute the first difference. Okay, first difference of the chain code, then we will get the differential chain code, and we will make it the rotation invariant and independent of. So this basically, this difference chain code is rotation invariant, and we will make it the independent of the initial point, okay, that we have chosen here. So the differential chain code will be invariant to initial point, and that code will be called as the shape number. So there we have to consider the maximum or minimum number obtained using this differential chain code, okay, in the circular manner. Okay, next we will discuss the Fourier descriptor. So suppose these points are the boundary points of any shape, then Each boundary points can be represented as a Cartesian coordinate as x, y. Okay. So here, let us consider that the boundary pixels of an arbitrary shape, okay, so whatever the shape we have, the boundary pixels are x0, y0, x1, y1, okay, x n minus 1, y n minus 1 if we have n number of boundary points, okay, or we can write x k plus j yk, and this will give us a complex number. That means this Cartesian coordinate is converted to a complex number with this representation for k equal to 0, 1, 2, 2, n minus 1 because we have n number of boundary points. Then we can take the Fourier transform, discrete Fourier transform of Sk, okay. Then we can compute Au of this complex number, okay. So we can write the discrete Fourier transform of Sk as, so like this, because here n, because we have n number of points, okay, k equal to 0 to n minus 1. So this is basically our Fourier transform. Okay. So you can note down here that if we will compute the discrete Fourier transform of a number, then it gives a complex number, okay, where the real component and the complex components will be there. That means AU will be a complex number. It means A1 plus JA2. So it will have real component and the imaginary component, so that we can construct a feature vector as A1, A2. So just you can observe here that these boundaries are converted to the set of the feature vector. Okay, because it will be also set of complex numbers. Okay, so that means for each boundary pixel we will have one feature vector. Okay, so this is the thing that just now we have discussed. That means the each coordinate pair treated as the complex number, okay, for n number of points, and then we computed the discrete Fourier transform, okay, using this expression, and where AU are the basically called Fourier descriptors. Next, we can compute the statistical moments of a set of numbers. Usually we compute the statistical moment of a distribution, okay. If we have any probability distribution function, then we can compute these statistical moment of that distribution. So if we have the boundary points and if we can convert it to the probability density function, then we can compute these parameters, these descriptors from this boundary pixels. So how we can compute the probability density function from these boundary points? So what we will do, we will find the extreme points and then will join it, and it will be our x-axis, where it will be our random variable. Okay, and we will compute the height of each boundary pixel, okay, for these positions. Okay, so here we will compute those values and we will normalize it so that g of r, or we can say that it is the probability density function, so that the summation of p of r for r equal to 1 to n. Okay, and this will be 1. So all the values will be normalized in such a way that the summation of all the values will be 1, so that it will become our probability mass function, because this is the discrete values. Okay, then so that will become our probability density function, and we can compute the mean and the other statistical moments like variance, skewness, kurtosis. Okay, so when here n equal to 2, it will be variance, n equal to 3, it will be skewness, when n equal to 4, then it is called kurtosis. Okay, so these are the basically the higher order central moments. We will solve one problem on this statistical moments. Okay, but first we need to discuss the topics, different topics. Okay, now let us discuss the regional features or regional descriptors. So just before we discuss the boundary descriptors, from this diagram you can observe that here there are the two image, okay, captured from the same body organs. Okay, and these two images captures the liver, and one image is captured using the CT scan, and other is basically the ultrasound of liver. Okay, and if we have our objective that we want to segment this liver from the other body parts, then definitely we have to focus on the region of this liver. So when we will consider the two different imaging technique, then you can observe here that the texture of liver in CT scan and texture of liver in ultrasound, it is totally different. Okay, that means their textures are varying when we change the imaging technique, and also its texture is different when it belongs to two different body parts. That means this texture is nothing but the regional feature, and if we will extract from the textural feature from these images, then it will help us to segment this liver from the other body parts, so that we can use the segmented liver for further processing or for the detection of different types of diseases. Okay, so there are many regional descriptors. Okay, so as we had the regional the boundary descriptors like length, perimeter, here also we have the regional descriptors like area of region. Okay, so it will compute the number of pixels enclosed by the boundary, or enclosed by the boundary is nothing but the region. So that is the area. We can compute the perimeter of region. So it will compute the number of pixels or length of the boundary. Okay, number of pixels on the boundary or length of the boundary. The other simple descriptor is compactness of a region, which is defined as the perimeter square divided by area. And the compactness of region for a circle is minimal. Okay, suppose we have a circle. Okay, then we can compute the compactness of region as the perimeter square. So for this circle, perimeter is 2 pi r divided by area. So we have to square it first, and divided by area pi r square. So it will be 4 pi. Okay, so this is the compactness of region for circle. Similarly, we can compute the compactness of other shape. Suppose we have square, then we can compute 4a square. So this is the perimeter square divided by area. So it will be 16. So here you can notice that 4 pi is less than 16. So as I told you that the compactness of region for a circle or disk, it is minimum. Okay, we can define the other descriptor, okay, other descriptor of compactness, and that is called the circularity ratio, and that is defined as the ratio of the area of region to the area of circle. Why circle? Because circle is a compact region which has the minimal compactness of the region. Okay, so we can normalize with the area of a circle. Okay, we can define other descriptors as mean, median. So whatever the numbers we will have, we can compute the mean, median, whether it belongs to image or one-dimensional signal. Okay, if it is image, then we will have number of pixels. Okay, and we will compute the mean of all the pixel values. That will be our regional descriptor. We can compute median, we can compute the minimum value among all these pixel values. We can compute maximum gray level values, or we can also compute the number of pixels with above and below the mean. Okay, so there are many ways to compute the regional descriptors. So these are the basically features, and we can combine these features to make it the feature vector. We can have other color features, okay, like RGB values, HSV values, and this is also LAV values. Okay, so these are basically the different color domains. Okay, that means whatever the image we have, color image, we can convert it to the other domain so that certain features will be highlighted, which is not highlighted in RGB. It will be highlighted in the other color domain. So these are basically the regional features. So colors are regional features, intensity, and also the textures as we discussed. So in medical image processing, textures are very important to study, because we have seen that in medical imaging we have a very strong motivation to consider the texture of the different regions to segment the different body parts. Okay, on even not in the medical imaging, even in real life also, you can think of the tiles and the marbles. Their texture is totally different. What is texture? Texture is nothing but the repetitive patterns. Okay, Texture is nothing but the repetitive patterns in an image, and if we can find that repetitive pattern, okay, some kind of features related with that, then we can separate those type of images. So let us study the textures. Okay, so there are different types of textures features, okay, which will focus on the region and the content of that region, how the pixels are oriented with respect to each other. So we can extract the texture features in the spatial domain and also in the transform domain. And the spatial domain, further, it is classified as structural features and statistical features. So just we have seen the statistical features like moments, mean, variance, kurtosis, okay. And the structural features are very specific, like linear binary pattern, wavelets, okay. So there are many features that we can extract from the images. In the transform domain, the image will be transformed to another domain, maybe using some kind of filtering or Fourier transform or some other transform. That means it will transform from spatial domain to other domain. So Gabor filter does that, okay. It transforms from spatial domain to frequency domain, okay. So in this lecture series, we will cover gray level co-occurrence matrix, linear binary pattern, and histogram. That means only histogram we will see, and how we can compute the statistical features. You may explore these topics, okay, by own. You may study the wavelets in image processing and some advanced version of the histogram. You can further study to compute the orientation histogram, okay. So first, let us discuss image histogram. How the histogram is defined. Here, the histogram of a digital image with intensity level in the range of 0 to L-1 is a discrete function which is given by this expression. So histogram is nothing but the frequency of occurrence of the intensity levels, okay. So suppose we have an digital image and we have the intensity level in the range of 0 to L-1, and here L is defined as to the power B, where B is the number of bits, okay. Means if we are dealing with 8-bit image, that is the grayscale image, okay, then to the power 8 will be 256. That means intensity level in the range of 0 to 255. That means whatever the intensity value, whatever the grayscale value will be, it will be in this range, okay. Then we will count that what is the frequency. Here n is the frequency, that means number of count of intensity level Rk, okay. That means suppose in our image the intensity level 0 is repeated, suppose 15 times, so it will be 15, okay. So the height, that means the frequency of occurrence of the 0 intensity will be 15 times, okay. Suppose if we have counted the intensity level 1 6 times, then we have to draw our bar up to 6, okay, at 1. So in this way we can count the frequency of occurrence of the gray values up to 255 if we will deal with the 8-bit image. Okay, so it depends that how many bit we are considering. Okay, how many bit image we are considering. Okay, so in this way we can compute the histogram. So histogram is the frequency of occurrence of the intensity level in the image. Okay, so it gives us a global information. Then we normalize the histogram with the total number of pixels in the image so that it will become the probability density function. Okay, so that the PRK is an estimate of the probability of occurrence of intensity level RK in an image. Same thing. So let us solve this problem to compute the histogram. Okay, so in this image, what is the maximum intensity value? So here we have the maximum intensity value is 11. Okay, and what is the next power of 2? Okay, what is the next power of 2 number? That means we have the power of 2 as 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. Okay, so see, this 11 is in this range. Okay, so we cannot choose the less number of bits. Definitely we have to consider the next higher bit. So we can consider here that this image is 4-bit image. Okay, so what we do, first we find the maximum intensity value present in the image, and then we find that what is the next power of 2 so that it can accommodate this intensity value. Okay, so we can say that this image is 4-bit image. So our intensity value will vary from 0 to L minus 1, and it will be 0 to the power 4 minus 1, and it will be 0 to 15. Okay, so that is why on the x-axis we have RK and the intensity value is varying from 0 to 15. Okay, the next step is to compute the histogram, that is frequency of occurrence of the intensity value. So in this image we have to count that how many times the intensity value 0 is repeated. So here 0 1 times, and there are no zeros here. So the height of this bar will be 1. Okay, the next intensity value we have 1, so we have to count that how many times this intensity value is repeated in this image. So let us count that. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So that is why here the height of this bar is 15 at intensity level 1. So in this way we can count all the height for these intensity values. Okay, that means we have to count the frequency of occurrence of all the intensity values, and we will plot in a bar chart. Okay, so this is called bar chart. Okay, so this is our histogram. So from this histogram we can compute our probability density function. So the probability density function PRK is defined as NK divided by MN. Okay, so let us compute. Probability density function is PRK equal to NK divided by MN. Okay, so in this image m cross n, so which is 7 cross 7. Okay, so this is the dimension we can put, and we can put the values as well. So this is 1, okay, this is 15, this is 5, this is 8, 4, 4, 3, 4, 1, 2, 1, 1, 0, 0, 0, 0. Okay, so these are the counts of these intensity values. So we can compute the probability density function. So P0, if you will compute the P0, then it will be the number of count 1 divided by 49. That means 7 into 7. Okay, and it will be 0.0204. P1 will be 15 divided by 49, and it will be 0.3061. So we can compute P2 0.1020, P3 equal to 0.1633, P4 equal to 0.0816, P5 equal to 0.0816, P6 equal to 0.0612, P7 equal to 0.0816, P8 equal to 0.0204, P9 equal to 0.0408, P10 equal to 0.0204, P11 0.0204, P12 is 0, P13 is also 0, P14 is 0, P15 is 0. Okay, so you can verify all these probabilities values for different intensity levels. Okay, now suppose we want to compute the statistical moments. Okay, suppose first we want to compute the mean value. Okay, and what is the mean? So here we are computing the statistical mean. Okay, keep in mind. So suppose we are computing statistical mean. So Zi into Pzi, and where I equal to 1 to 15, or sorry, I equal to 0 to 15. Okay, so here we have used the notation, if you remember. Okay, Zi is nothing but the Rk. Okay, so here Zi is the count, that how many times. Okay, so we have 1 into the frequency of occurrence of the intensity value 0 is 1. So 1 into the probability of occurrence of intensity value 0. So we will write like this. Okay, plus the next frequency of occurrence of intensity value 1, it is 15, into the probability of occurrence of intensity value 1. So it will be 0.3061. So in this way we will compute all. Okay, then we will obtain 3.6327. Okay, so this is basically the statistical mean. Okay, similarly we can compute the variance. Okay, so for the variance we have Zi minus mean that we have just computed. Okay, square Pzi, where I equal to 0 to 15. Okay, So when you will put, this value will come. So when you will put, this value will come 7.6610 skewness. Okay, so here n will be 3. Okay, I equal to 1 to 15, and this value is 18.3. So you can verify these values by calculating at your own. So we can compute the kurtosis. When n will be 4, it will give you the kurtosis. (166.6847). So here these parameters are basically considered as the feature components, and we can make it in a vector so that it will be feature vector, and that can be used for the representation of an image, or we can say that it can be used as a global feature of an image, so that we can use it image classification problem. Okay, so this much for this lecture. If you have any doubt, you can ask in the comment section. Thank you.